Machine learning is revolutionizing physics in incredible ways. It helps us uncover hidden patterns in complex data, making it easier to analyze phenomena that were once too intricate to understand. For example, in particle physics, ML algorithms can sift through massive datasets from experiments like those at the Large Hadron Collider, identifying rare events that could lead to groundbreaking discoveries. Simulations, too, benefit immensely. ML accelerates these processes, allowing us to model systems more efficiently. If you're a physicist looking to integrate ML into your work, start by familiarizing yourself with tools like Python and libraries such as TensorFlow or PyTorch. Online courses can provide a solid foundation. Embracing machine learning not only enhances your research but also opens up new avenues for exploration in the vast universe of physics. Machine learning is revolutionizing physics in incredible ways. At the Large Hadron Collider, it sifts through petabytes of data to uncover rare events like the Higgs boson. In fields like condensed matter and astrophysics, ML approximates solutions to complex systems that traditional equations struggle with. It even accelerates simulations. Neural networks can replace slow numerical solvers, enabling real-time predictions. Plus, tools like AI Feynman are automating the discovery of physical laws from data, and in quantum mechanics, ML aids in state reconstruction and control. The future of physics is not just in equations, it's in the data-driven insights that machine learning provides. In the world of physics, machine learning is revolutionizing how we analyze complex data. For classifying particle events, neural networks and decision trees are game changers, offering precision in chaotic environments. When it comes to pattern recognition in images like those from telescopes, convolutional neural networks shine, extracting meaningful insights from vast cosmic data. For time series predictions such as solar activity or gravitational waves, recurrent neural networks and LSTMs excel at capturing temporal dependencies. Feature extraction in large datasets, autoencoders and PCA streamline that process, making sense of the overwhelming data. And when physicists seek to uncover governing equations, techniques like symbolic regression and genetic programming come into play. Finally, for simulation speedup, Gaussian processes and deep neural networks are paving the way for faster, more efficient computations. The fusion of physics and machine learning is not just a trend, it's a powerful partnership reshaping our understanding of the universe.
As a physicist diving into the world of Python and machine learning, start with the essentials. NumPy for numerical computations, Pandas for data manipulation, and Matplotlib for visualization. Once you're comfortable, explore scikit-learn for basic ML models. Then level up with TensorFlow or PyTorch for deep learning. Take Andrew Ng's ML course on Coursera or check out fast.ai for practical insights. Get hands-on with public datasets from CERN or the Sloan Digital Sky Survey. Tackle projects like classifying galaxies or predicting pendulum dynamics. In astrophysics, focus on exoplanet detection. In condensed matter, simulate phase transitions. The possibilities are endless. Embrace the challenge and let your curiosity lead the way.